Hello. So this is 27th of February 2025. It's been long since I last posted here. Yeah, but I think I'm in need of this right now. I just want to talk through things, type through things, write through things. Um, so finally, I'm getting to do a course on differential geometry, a very great course in differential geometry, very abstract, very intuitive, and very rigorous. So things have been very hustly bustly in the last few weeks, but I've been trying to do some nice things amidst that. Um, so yeah, I mean, okay. So right now I have a mid-semester exam on 3rd of March. So it's like 4 days roughly. In 4 days, and there is a good marker of the half of the quarter semester when I had a take-home quiz for the course. Um, we read till submanifolds, embedding submanifolds, immersions and submersions and all that until that point, and after that we started tangent bundles and then vector bundles, sections, vector fields, and integral curves. So after that quarter semester mark, I decided that I really like and want to type through things, take these notes properly, right? And the instructor is teaching it beautifully. The instructor really gives you that intuition, uses a very abstract language, proceeds with things very rigorously. It's a jackpot. It's an all-in-one jackpot, and yeah, with that comes a great responsibility from the student to fill in the exercises, fill in the class exercises, and fill in the details, fill in the gaps. So I've been trying to do that, but it's very yeah, it's very tricky to do that. And yeah, I mean, it's really nice to work immediately after the class and take notes and work through the details after the each lecture, rather than piling up all the lectures. It's very hard to do that. That's what I'm realizing right now. So yeah, I already started taking my notes. As you can see, I started taking notes. So I have these notes on tangent bundle. We define what tangent bundle is union of all the disjoint union of all the tangent spaces. Then we try to look at the potential charts on it, right? Then we try to give a topology on this tangent bundle, basically lifting the topology from the um, from the local from the manifold, the shards of manifold M cross Rn, because locally the tangent space is that. And yeah, we try to lift the topology from there, but taking basis from there, and we try to prove that this is indeed Hausdorff second countable. And yeah, it basically defines an even a smooth atlas if there's such collection of such charts from a smooth atlas on Tm. The projection map Tm is smooth, is a continuous map. In fact, it's a smooth map. And yeah, and then basically we have that Tm is a 2-1 dimensional smooth manifold where n is the dimension of the manifold M. And then we saw that tangent bundle is actually a special case of we noted that tangent bundle is a special case of vector bundles where we attach vector spaces to each point, and we define what vector bundles are. It had 3 levels of definitions. It is basically a smooth surjection from the total space V to a base manifold M. It's a smooth surjection. Then the fibers are vector spaces of dimension k. By fibers we mean inverse images of points in the base space M. Pi inverse P is a vector space of dimension k. It's called the fiber at P. And then these vector bundles are locally trivial in the sense that, and by trivial we mean that these are just locally are from U cross RK, where U is a neighborhood is a neighborhood in M containing P. Yeah. So yeah. So it's locally basically you are attaching to each point a dimension k vector space, right? And what really happens is that the vector bundle, the total space is diffeomorphic to U cross RK, and along with the fact that the vector spaces VQ, which are vector spaces of dimension k, are precisely isomorphic to RK at each point. Right, it's a linear isomorphism. So H is also a diffeomorphism from pi inverse U to U cross RK. It is also a linear isomorphism from the fiber to the Q cross RK. And what is interesting to note is, well, I can't read out every details right now, but the dimension of total space is dimension of M plus K. It's a, yeah, and in fact pi is a submersion. It's a, by submersion it's a prototype of projection map, right? In fact it is indeed, because you have this local trivialization, and local trivialization the projection U cross RK to U is in fact a submersion, yeah, that's how even pi, the pi inverse U to U is a submersion. Pi V to M is a submersion. So it's sort of a projection map. It's a prototype of projection. It's good that it follows. And then local trivialization. This image summarizes it intuitively. At every point you're attaching these vector spaces, and locally it is isomorphic to U cross RK. And some examples: the trivial vector bundle, manifold M times the RK product manifold. This is trivially a vector bundle. And then we have the tangent bundle that we defined just before, which are basically attaching the tangent spaces at each point, which are again some k dimensional vector spaces at each point. And yeah, these are also vector bundles. And some really non-trivial example is the Mobius bundle over Mobius bundle, which is basically the Mobius strip, and it can be realized as a bundle over the S1 over S1. This image sort of clears the intuition around it, right? But making it formal is a really nice exercise. If you mostly rely on this quotient mapping here, S1 cross R to S1 is a projection map, and you quotient out using the relation ZT is equivalent to minus Z comma minus T, C2 action on S1 cross R. So this gives this map quotients through to M Mobius strip and gives a mapping pi from M to S1. Now our claim is that this pi M to S1 is the vector bundle. Since pi tilde, pi hat or pi tilde is e per pis and smooth, pi will also be smooth, and then the fibers are precisely the plus minus Z cross R, but identified. But you don't have two copies of R. In fact, these are identified by plus z comma t and minus z comma minus t, so it's isomorphic to this R. So you have the fibers, or you have R fibers, if you could say that. And then one need to be careful and look for the local trivialization. Yeah, it's really made formally here. You can use the picture to sort of summarize all this. So you start from S1, you left out a pi inverse of, you take a chart U plus, right? Pi inverse of U plus would be basically S1 cross R, right? So pi tilde of pi tilde inverse of U plus is something like this. Here, yeah, right. So yeah, note that the pi tilde map is actually yeah, this pi tilde map is actually z comma t to z square. Okay, yeah, I should write this down here. Okay, I should write this down here. Okay, so pi tilde. Okay, I can just write it in the caption, maybe. Pi tilde pi of z comma t equals to z square. Yeah, this will work. Yeah, so so pi tilde inverse of U plus, and this the map pi. If you see, these 2 points will be removed, and then yeah, you can consider open set this, which is basically diffeomorphic to again U plus cross R, right? Then the diffeomorphism quotients through the quotient map, which is a local diffeomorphism. In fact, Q is a local diffeomorphism, but from U V plus to Q of V plus is a diffeomorphism, and then they have a diffeomorphism from this pi inverse of, in fact, U plus to U plus cross R, right? That way it's just neatly follows, right? This is just the formalization of everything, and it's not that abstract either. It's nice. Yeah, similarly take U minus and things will work out the same. The interesting part is that the maps S1 cross from S1 cross R by tilde to S1 and minus 1 cross R tilde to S1 are same maps given by both the commuting diagrams here, and yeah, that's something good to check. And also note that there is some sort of orientation involved in this that is making this Mobius bundle non-trivial. Actually, will in fact show that Mobius bundle is indeed non-trivial. It's not isomorphic to the trivial vector bundle over S1, right? Yeah, and yeah, it is true that I didn't fix the understanding around how S1 cross R over tilde is diffeomorphic to the Mobius strip M defined by -1, 1 closed cross R by tilde. That is something I need to do, go back and do. Okay, that is good. Mobius strip is a vector bundle over S1. In fact, it's a non-trivial vector bundle over S1, and you see that there is an orientation involved. Yeah, that is making it kind of non-trivial, right? The moment it's not orientable, I think the space becomes, the vector bundle becomes non-trivial. So the question is, what if there are two twists in the Mobius strip? Yeah, we'll probably think about that later. And also there's an interesting result that over S1 there are only two vector bundles of two diffeomorphisms apparently. So there is either a trivial vector bundle or a Mobius bundle. Interesting. So if there are two twists in the Mobius, if it's a two twisted Mobius strip, then I'm not sure what's going to happen, right? Is it a trivial vector bundle or okay, I think it's isomorphic to Mobius bundle itself, because is it orientable to one twisted? It's orientable and it's not trivial. You see, that is something to think over. Now comes to the, let's go to the tautological line bundle over the real projective space RPN. So recall that we define RPN via all the lines in Rn plus 1 passing through origin, basically, right? You identify all the lines, different lines passing through origin. By different, basically we mean different slopes, and all the lines, basically, all the points on a line are equivalent. Beautifully, this is also diffeomorphic to Sn quotiented with the C2. You identify the antipodal points in Sn. This is the exactly RPN, right? And RP1 in fact is just the S1, because in S1 if you identify all the antipodal points, you get back the S1. That is beautiful. Again, and S2 you get sort of a upper hemisphere with the equator points antipodally identified. That is something relevant to a bit earlier discussion, pre-quarter sem, and it's good to fix that understanding also. Let's go ahead for now. So we'll define this space called Ln, where we attach to an equivalence class of all this of a line. Basically, all the points in a line corresponds to one equivalence class, and to that we'll attach all the points on the line, right? Basically, it's the span of the equivalence class, if you will, if you wish to call it like that. So let me check if it's actually recording. It is recording. Cool. So to every point you're attaching a vector space. In fact, it's a one-dimensional vector space. This varies. This vector space varies, at each point, and it doesn't look like a trivial vector bundle, right? Okay, so so our claim is that it's a vector bundle over RPN. Intuitively makes sense because we're attaching some one-dimensional vector space everywhere, and with the projection map Ln to RPN, simply just ditching the second coordinate. So let's define topology on Ln. In fact, I think it's natural to define the topology via letting pi be continuous, right? Define the topology on Ln. In fact, it's almost provides a unique topology, and in fact, topology Ln by demanding pi is continuous. So the open sets in Ln are precisely the open sets in RPN cross open sets in I mean, yeah, it's u0 times all the span of if you remember the charts in RPN, they are from UI to UI. At each point you attach this vectors, one-dimensional vector space. That's your sort of open sets in Ln, and in fact we'll define the charts in the exact same way. Define the charts on Ln as follows. Define the charts as follows. So what will they be? I'm going to refer to my board work. So I'm gonna define the charts as this. So phi from tilde, sorry, not why did I tilde it? Phi pi inverse UI, remember the chart on RPN. To what will I do is precisely make use of this phi 0, which let the phi 0 be the chart map for UI times R, which will be a subset of Rn plus 1. Okay, I should have actually gone ahead with an aligned environment. So that would give us yeah. So how are we going to define this map? We will basically write it this way. The first coordinate, remember, it's just the chart on RPN. In fact, hat Li, remove the Li coordinate, N. Okay, apparently Ln by Li. Note that Li is non-zero because we are in UI. So L0 by Li. So then the last coordinate is going to be Vi. Okay, this is interesting. This will work out apparently. Right, that's how we're going to define this map. Okay, what the hell did I do? First thing, of course, I want to map it, align it. I'm not sure. Okay. So I think this is the space. This is space. Cool. Right, so this is indeed injective because this is injection. Okay, let's just say injection. How? Because phi of L comma V equals to phi of M comma W implies if and only if, I think, of course L has to be M, so L is a multiple of M, and Vi has to be Wi, right? But Vi is precisely a multiple of L, Wi is a multiple of M, so they are multiples of each other, and this Vi equals to Wi fixes the multiplication factor to 1, so V has to be W, so implies V equals to W. So this just says that it is injection. How do you say it's a bijection? Sorry, it's a surjection. Okay, yeah, surjection is simple. If I don't know, yeah, m1 dot 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 m underscore n plus 1 is in n plus 1, Rn plus 1, right? Then our claim is that our claim is that then phi of, just take the classic route of defining the first n coordinates to equivalence class in Rpn. Then what you do is mn plus 1. Okay, let's bracket up mn plus 1, and then you divide by precisely mi. so that you get the multiplication factor out. Then you multiply by, because mi is non-zero again, mi is non-zero, then you just multiply by m1 dot 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 comma m underscore n. Got it? Wait, what? Wait, what? I think I did something wrong here. Yeah. It's actually, it's just one. Yeah. I mean, we are going to m1 so on up to m underscore I minus 1 comma 1 dot 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 n. This is fair. Right? Oh yeah. Okay, so you have to put the ith element as 1 so that you can divide by stuff. So m1 so on up to mn, then you put a 1 in between. Right? Ith element is basically 1. Right? And there is mi plus 1, so on to n. So if you divide by 1, m1 minus 1, m1. So then m1 so on up to same thing. Lot here the ith element is 1, yeah? Doesn't make sense to sort of yeah, here I'm saying that it's just you don't know that MI is, you don't know that. You don't know that. Precisely. Yes, you don't know MI is 0. One comma then for I the dot same thing. Okay, so phew. Yeah, the claim is that this is the this is indeed m underscore 1 dot m underscore m underscore n plus 1. That's the claim, which is true. And we need a write. So yep, that is there. So the charts are defined. So that is indeed a surjection. The transition functions. The transition functions for this will be basically rescaling some of the last coordinates actually. Sort of. Oh wow, what? Yeah. I mean, transition function, now it's easy to check the transition functions at this point. Let's not write them out. It's easy. The transition functions are easy to. The smoothness of transition functions is easy to check. Easy to check to do definition, and indeed the fibers are already isomorphic to R. Now what we need is a diffeomorphism. Okay, so how do you give out this diffeomorphism? Is so you want the diffeomorphism. It is the diffeomorphism is trivial because the local trivialization is follows from the charts. Yeah, precisely follows from the charts because yeah. Yeah, local trivialization. The local trivialization can be simple to write. It's simply let's align it, is simply phi pi, okay, wait, phi pi inverse of ui to simply ui times r, right? This is very simple to define, very simple to define as follows. What you do is take L comma V to precisely the same L identity over the first coordinate and the ith coordinate. Let's take the ith coordinate, and this defines our, this basically defines our okay, for now, okay, I mean, okay, let's fix this error. Okay, let's first fix the local trivialization. So this is indeed a local trivialization, I mean, because it is basically a composition of the diffeomorphisms, the charts and the charts of ln and charts of ui are simply diffeomorphisms. The composition of charts in ln and the charts in rpn. Yeah, simple. As a composition of charts, diffeomorphisms, over RPA, rank one for line bundles. So that is established. In fact, now the important, interesting point is that in fact ln rpn is a submanifold, it's a regular submanifold of len through the following. So what are the adapted charts here? So we don't have to give that. Yeah, I mean, okay, so the same, okay, yeah. In fact, it's a regular submanifold, as which can be seen from the charts in ln, letting Vi equals to 0. Regular submanifold of Rpn, which is precisely we take V as the pi inverse Ui. Okay. Oh yeah, we can just take which can be seen from the chart symbol I. V a subset of pi inverse of Ui as a let's first write equals to L comma 0 mid Li is not equal to 0 and L belongs to L in n plus 1 is a subset of n is a subset of subset of R P n. Yeah, it's an open subset of R P n, and right. Which is precisely equals to phi inverse of Rn times 0. Well, so union of charts, right, which can be seen from the charts in phi I in fact this is precisely UI. I mean, I bit of twisted things there because I don't have to actually subset of. Anyway, we established that it's a regular submanifold of Ln. Okay, now let's fix the. I know it's a slow process. So what can I change here? I don't see anything, but let's just put 2 dots, right, instead of 3 dots, and see what happens for a change. What the hell? 354 to 355. What happened? Are you saying I just messed up? Works wonders, huh? Okay, so cool. We just established that in fact Ln is a rank 1 vector bundle over Rpn. It's, I don't know, it's called tautological line bundle. It's like to a quotient space you're attaching all the elements of the quotient space. To a quotient space you're adding in at each point all the elements of the equivalence class. That's sort of a tautological vector bundle, I suppose. If it forms a vector space, of course. I mean, yeah. I think this sort of works for similarly to other quotient manifolds when you quotient out vector spaces at each point. In fact, yeah, that is interesting. Get to note. So yeah, and it's a rank 1 vector bundle. Now the interesting thing is the interesting thing here is that how do I write it? Exercise okay, so interesting thing is L1 is exactly the Mobius bundle over S1. Exactly the Mobius bundle. So one can proceed in two ways here. We define what are vector bundle isomorphisms soon, but I think we can go with something like the very set L1 is in fact. Acha, you can say that L1 is a diffeomorphism between S1 plus R till quotient C2 and yeah, L1 and S1 cross are push. L1 and Mobius strip are diffeomorphic. You can prove that actually. So I'll just give the diffeomorphism is exactly the obvious bundle over S1 because note that RP1 is diffeomorphic to S1. Okay, so I won't give you diffeomorphism here. I worked out the details in my notes. I can actually write it here when I have the notes. Now I won't go through the details of it. It is simple though, right? You just have to write things down explicitly locally, and you just it's easy to show that. I mean, yeah, it's easy to show that. Yeah. Things, yeah. In fact, we will define the notion of vector bundle isomorphisms the exact same way. We have a diffeomorphism in the total space, and both of them are vector bundles over a similar manifold, same manifold S1, same manifold M. Then it's basically a such that the diffeomorphism along with the projection maps commute fiber to fiber. There's a one-to-one fiber to fiber mapping. There's a bijective fiber to fiber mapping. There's a one-to-one. Okay, there's a yep. Not one-to-one fiber mapping. There's fiber to fiber mapping, and yeah. Okay, so I was stuck here for a long time actually. Okay, now I'll add this detail soon, later sometime. Okay, what next is that now that we have shown a couple of things, I mean, yeah. Yep, now we define the homomorphisms of vector bundles. I think it's a good subsection to start. Homomorphisms of vector bundles. Okay, so begin definition is okay. Before I do it, let me pause here and see how it goes, how it is going here. It's already been 1 hour, so I'll just